Yeah. Further. How are things? How are things going?
Okay.
Okay. Is it getting busy or is it getting relaxed?
It's getting busier.
Busier, I see. How many courses are you guys taking?
I'm doing 3 courses. So two, one is the research credit. So I don't have to take classes right now. But I have teaching duties and grading.
Correct.
Correct.
And you're taking this course and which other course?
I am teaching 253B.
53. And which is the other course you're taking?
Electrodynamics.
Electrodynamics. Okay. Bamsu.
Yeah.
What about you? Same?
Same electrodynamics and
Are you teaching?
teaching as
Which one? 253.
and I have another one, 101.
101. Okay.
And
You're
grading,
teaching or
teaching.
101 you're teaching?
Yes.
The lab?
Yes, yeah.
Okay.
And I have grading as well and lecture.
Okay. See if you can a minute, maybe. So we have homework 2. That was announced wrong last time. Yeah, now it's correct. Unless I'm not able to finish anything at all today, I think it will be due on Friday. And then we can do curvature and other quantities on Friday. Okay. And there is a midterm 1. So that might be a homework 3 and a homework 4. So midterm 1. Away. Well, it's expected that there will be a homework 3. Also, assuming each week we have a homework. That's go. Any idea, Ken? Okay. Give it a minute. Yeah. Since we are only 3 people, we can wait. So no research for you, Abhiyan? Research credits? So you're taking 2 courses, and so you're enrolled only in 6 hours.
Yeah, I have 570.
With
No. With Professor Cycle. That's
this
to
is
credit.
yeah, but this is the introduction to
Yeah.
like you have to meet everyone, correct?
Yeah.
And what about you?
I have the same, I mean, to credit with Professor Shaikar, which will talk to other professors to select next.
Okay. Okay. So you guys are not no lab work
Mhm.
yet, right?
Yeah.
Yeah, good. Yeah, that you should take it seriously because within a semester or so, earlier you start your work, better it
Yeah,
is.
I
And you
agree.
don't have to wait till the end of the semester.
Yeah.
If you really know what you want to do, then you should start working earlier. That's advice.
I think I'm thinking about deciding this week.
This week, okay, that's pretty good. Very good. Yeah, you guys should also. You should also
Yeah,
put your
I also
effort.
think about that.
Yeah. So that's good because like both of you must have taken these courses in some form before, right? Have you done a master's?
No,
for
I
that?
never did the master's.
Did you do that? So how many years of bachelor's did you do?
4-year bachelor.
Okay, so in Bangladesh it's a 4-year bachelor's.
Yeah.
Okay. So and what
I
about you?
did master.
Master's, yeah. So you must have seen these courses
Yeah,
in
I
some
have-
form before.
Yeah, I've seen, I studied, but
Yeah, of
I'm
course.
getting updated now.
No, that's good. Yeah. And which universities are you from?
I'm from University of Chittagong.
Chittagong. Is that north?
Yeah. No, not
North of
Chittagong.
Bangladesh. Okay. Yeah, I don't have very good geography sense of Bangladesh, but roughly, yeah.
You ever been to Bangladesh?
No, not Bangladesh, but I lived in West Bengal
Okay.
for quite some time. So I know Bengali. Yeah. So I stayed for 2 years there. Yes, good amount. Yeah. But Nepal, I've been to Kathmandu for some reason, but just as
I did from
couple of days.
Tirubhuvan University.
Which
Tirubhuvan University.
Tirupur.
That is the,
Do you have is anyone from that university here?
yeah, most of them from same
Most of
university.
us from the same
And that
university.
is the main and large university.
Large university.
I think Yuvraj Sapuda is from India
Okay.
and others also from same university.
Same university. How many big universities in Nepal would you know?
Altogether 7 universities,
Seven. Okay.
but they have different tracks.
Got it.
Tirubhuvan University is the larger one.
Good. And probably more resources also.
Yeah.
It's good.
And it is in the capital city, Kathmandu,
Kathmandu.
and most of the students come there. And
Good.
I need one suggestion about.
Sure.
I'm actually getting confused to how to select a particular field for my interest. I don't have much research experience earlier, so sometimes I feel like I will go for experimental field, and another time I feel like I should go for a theoretical field like quantum information or something. But I am sure about one thing that I am interested in a theoretical field. But the issue is I am not sure about my mathematical skill will allow me to go for a theoretical field. I don't feel like I have the capabilities, mathematical sense to actually go for a theoretical field. So today I am thinking about going to this field, and tomorrow I am
Changing. Yeah. That is reasonably natural. I mean, at least in an early stage, if you don't know, but still, since it's going to decide it's a big decision, you should take your time. And here is how you might give it. I mean, this is a very personal suggestion. So typically in research, there is always an idea of challenge there, which I think all of us know, right? Which is what probably is the driving feature of that. And there is a job part. That's the two important things that people think of when you're doing research. But I think there's a third factor which plays a very dominant role in the whole of your research life, is that you will have to do the dirty part of research. And the dirty part of research is, let's say experimental physics will be that, okay, if you have an instrument, you get data and then you analyze. That's the good part, that's a challenging part. But to get that instrument working, there's lots of dirty work, right? It's like saying you have a car, but no mechanic. Think of you're having a car and you don't have a mechanic. Driving the car, if you enjoy driving the car, it's a good experience, but you might spend 90% of the time fixing the car or 99% of the time fixing the car. And for 1%, you will be able to drive the car. So same thing with research and most of the experiments, that is a good part of making sure that everything goes well. So it's like living a life where there's a lot of rules you have to obey. Only when you obey all this, you get a perfection and then you lose. And often we don't think of that dirty part. That's what I call the dirty part, where that's not the main thing, but it is very, very important. So you should enjoy that. If you're doing theory, you would say that, oh, there is no dirty part. No, that's not the case. Think of, let's say, if you go 400 years back, Newton wanted to calculate something, let's see, he invented calculus. He wanted to calculate the integral of square root of x or something, which is basically important for calculating the area of a circle. Right? Now, if he calculates that, then he has to calculate the value of pi himself. There was no calculator at the time, so you will have to do the dirty work of calculating pi to the 20th decimal. And you have to be very careful because no one else might have done it. So he wants to match the theory and experiment. So the dirty part there is that you'll have to do calculations, the really algebraic calculation, very tedious. And you have to be very careful in the sense, oh, if you don't cancel it, then it doesn't. So both requires a lot of meticulous work, a lot of care, a lot of patience. So between these two, like, can you, if necessary, would you like to calculate pi to the 50th decimal without a calculator, with a pencil and pen? And would you enjoy that? And if you make an error, that might decide your calculation. That's what you should ask when you want to go to theory. If you don't enjoy that, if you cannot imagine yourself sitting from morning to evening and doing a calculation which is really tedious and you feel that, oh, this is dirty work, then theory is not for you. Same thing for experiments. If you don't like taking the plier and a screwdriver and get curious about, for example, in your house, something is not working. No, I want to do it the other way. And you want to do something. If you don't enjoy those things, that means that's not the best thing you want to do. And of course, this is the extreme scenarios. Things are not like this. I mean, in real life, there's a mix of all this. But in some sense, there is this care, very careful things you have to do to get something else. That's what I feel is important in research. Does that help?
Yeah.
All right.
Is it possible to actually move from theoretical to experimental field? Experimental to theoretical.
In principle, yes. So the question is, okay, if you do this, our department is pretty small and pretty flexible in various things. So if you make the decision that, okay, within 1 year, I want to move, right? Inside our department, I think everyone is nice about it. In fact, when you're joining, you can tell that I want to figure this out. Or best thing is you join someone and say that, okay, kindly give me a small project, a very tiny part of the project. I would like to do this for 6 months or 1 semester and figure out whether I like it or not. You see what I'm saying?
Yeah.
That might be a good idea. Our department, I think everyone would agree. Is that clear what I said? Like approach them and say that I want to do a small project. I want to see whether I like it or not. Can you give me a tiny thing of something related? most probably they will not mind that, and they will be glad to do that. That's an easy switch. And then 6 months down the line, you change your field, and now you know that, okay, you don't want to do theory. But it's also possible that you can do theory or experiment for 2 years, or all for all of your masters. And then I don't know, are you guys for PhD or masters here?
I am from masters.
Same master.
Same. So you have a choice to make after 2 years. You can also apply outside, or you can continue, or you can apply here for PhD. So that's when you can switch. That's a reasonable thing to do. That's also not very late. It is okay to switch that. In fact, it is good. Like if you're doing theory, if you do your master's in experiments, and it's okay that you won't lose much. In fact, it will only help you in the long run. You might lose in the short run that, okay, your experience is a little lower when you're beginning, but in the long run, I think it's a very good perception to have. So 2 years is okay, but I think if you take 4 years to decide, I think, yeah, it's not necessary, but there are examples where people do this. A classic example is Pauli. Have you heard of Pauli? Pauli's exclusion principle?
Yeah.
Like the atomic
Enrico Pauli.
Yes, that's correct. Enrico Pauli was a Nobel laureate. There's this Fermi lab in very close to Chicago. It's named after him. He was a theoretician until the age of 32, 35. And then he switched to experiments, and he became one of the best experiments. So of course, ideally speaking, you can switch anytime, everything, but it'll be harder, of course, especially these days, things are so niche that if you don't have the experience, you lack your expertise in a sense. Like if there are 5 people, then others might have more. But if you're not interested in the competition, which is not necessary, there are so many things you can do these days. The competition really is not necessary. Then it doesn't really matter. Like you'll always be able to switch. And if you're not very extremely ambitious, then job also is not that bad to get. Okay, that's that.
Yeah, thank you.
Yeah. And feel free to talk to me. Like you can come to my office about this anytime. I can try to help, but this is the kind of information I can give. And again, all this is, this is all very, I haven't thought about it so seriously. So I'm just talking based on my daily experience. So you should give more weightage to your thoughts. Okay, but feel free to contact and come to my office. Okay, I think Ken may not be here. So let's see. Okay, so what we want to do today is broadly what's called curvilinear coordinates. And just to give an idea, when we think of so the examples, sorry, just to give a nomenclature of the whole thing. Examples are like, what are the coordinate systems we can think of? Rectangular coordinates. Good. So rectangular coordinates. And if you're in 2 dimensions, it's X and Y. If there is a 3rd dimension, it is Z. Just for simplicity, I think sometimes I'll work in 2 dimensions because 3 dimensions, since I want to introduce concepts, I might work in 2 dimensions, but it's expected that we should do everything 3 dimensions. So of course, there is cylindrical coordinates. And I will try to use rho. So this is the Greek letter rho, and phi for our angle, and this will be z. So you should be familiar with cylindrical coordinates, what this means in complex plane, which has sort of a lot of properties of a two-dimensional plane, but not completely. That's a significant difference. Also, the Argand diagram there is pretty much the same. And we have spherical coordinates. These are the three important coordinates of theta
Yeah.
and phi. Yes. Question? No. Okay. So that's here. One should be careful in this theta and phi. There might be some confusion. So what I use here is, so that's your z-axis, and that's let's say x and y. So that's my x-axis. That's my y-axis, and let's say this is my general vector. And if I were to if you think of this as a vector, that's my angle theta. Right. So that's your xy plane, and that's my projection of this in the xy plane. And the angle the projection makes with the x-axis is the angle phi. Is that clear? Now, what happens typically is that I didn't know about this until I started teaching, is that most of the mathematics textbooks apparently use phi for here, theta for here. And most of the physics textbooks prefer theta and phi. But of course, there is no, anyone can use any nomenclature you want to. But if it is not, there is no diagram specifying it, at least in this course, theta will represent this. But if you're used to using the other way, then make sure you switch. But again, always ask where the diagram is somewhere there. If you're reading a textbook, always look for a definition for that. Remember that z, if you have specified x and y, z is not always optional. For example, let's say this is your x-axis. That's your y-axis. Where is my z-axis? Is it going in or coming out? Or it doesn't, it does not matter.
Doesn't matter, it depends on the plane or
It doesn't matter.
this.
No, I'm saying if z in the rectangular coordinates, it has to be perpendicular to this, right? Now there are two vectors perpendicular, at least one line perpendicular to that. But when I put the direction, it can come out of the board or it can go into the board. Which one is it? Or it doesn't matter.
Clockwise, then the right hand rule or something.
Right hand rule, right? So it z has to be, z hat is always x hat crossed with y hat. Okay, so do the right hand rule, it comes out of the board.
Yeah.
Now, is this necessary? Yes. In all that we do, we have this notation. We work in a right-handed system. If you work in a left-handed system, that's okay. That like when you're defining, if you're writing a completely new treatise on your own, you're writing a book or something. Yes, left hand is okay, but then you have to change everything. So as far as almost everything, mathematics, physics, everyone, everywhere in science uses the right-handed system. Okay, so one should be, and that is no confusion, but one should be aware that the choice has been already made. Right? So z is coming out of the board. In this case, x crossed with y is z. So it's just a information there. But of course, even though these are the three important coordinates, and most of what we do in physics, there are very limited problems that can be exactly solved. it's even though we have achieved a lot, very limited problems we can solve exactly, right? Exactly, I mean that which you can actually express your answer in terms of known functions. So they're very less. And in fact, there are only 11 coordinate systems in which you can solve things. Those are all very limited geometries, which are really nice. But nevertheless, we should be able to do, I mean, this is a choice, right? Physics should not depend on a choice. Who cares whether you use cylindrical, or spherical, or any other coordinate? It should not. And we would like to do things in a general coordinate system, and that's what we want to attempt on, and how things will look like in that case. So let's draw a, or before I proceed to that, so let me introduce what is the idea of, if you use optics, geometrical optics, I think I should say geometrical optics. Geometrical optics is where you talk about rays, right? A light ray coming and reflecting off something before wave optics. And in geometrical optics, you have the idea of a wave front versus a ray. Okay, what does that mean? So let's think of a monochromatic wave. What is a monochromatic wave?
Single color.
Yeah, when you think of light with a only single wave, then a single wave is a single color. So for example, red color light, like that means it's a monochromatic wave. And actually, I want to not only say monochromatic wave, it's a monochromatic plane wave. So monochromatic here means that it's a single color wave. What does it mean to say that it's a plane wave? What do you mean by plane wave then?
It's confined in a plane of.
Yeah, roughly. But what is confined in a plane? So think of a source of light, right? And it can be imagined as its energy is going this way, right? This is a source of light. What does this dotted lines mean? That's one way of, so if you think of a stone that is dropped in water, there are these waves that go, and this is the way the waves might go. This might be at a time, if you were to take a picture of the wave that is coming due to the disturbance caused by a stone dropped in water, then it will look like this. It can also be represented by these lines, right? And this will be called a ray, and this will be called a wave front. Is that clear? Have you seen this before? Read this? No? Okay. In optics, this is the idea you will depend on. But I started by asking what is a plane? Okay, so let me define this better. Now, this is a point source, right? If you do a point, but now imagine there are lots of point sources. These are all point sources. Now, when you have a ray, so this will, if there was two point sources, the ray will be like this. If there were three, this will get extended, right? So if there were 2, 3, 4, let's say. So this will be spherical here, but then it will be flat here, and then this will be like this. Is that clear? This is how waves, if you have 4 point sources, will look like. If you extend this point sources on a whole line, then this will become a plane. This is your wavefront. So these are wavefronts. But the energy actually is not, energy is not, if you think of motion of energy, energy is moving perpendicular to the wavefront. Where is energy moving? It's going perpendicular to the wavefront. Wavefront is where you will see the actual physical wave going up and down. If you think of electric field is of a light is going up and down, but the energy is actually going in that direction. Right? If you stand here, you will get blasted by a wave, you will experience a momentum or a force in that direction. If you're standing here, you might move up and down, but that's okay. It might be less hurting in a sense. So this is your wavefront, that's your ray. Okay. And those are two different concepts, but you can use either one of them to explain something. For example, often you will say in quantum mechanics, especially, use something a wave or a particle. Both are okay, we know, and similarly, duality, exactly. So here, if you have a concept like this, especially light, you can either explain it using describe it using a wavefront. That's good. So these circles are good enough representation for a point source. But these rays of light are also good enough to describe a point source. And both have its own power or its own advantages and disadvantages. Okay. So I should give a quiz on this. So this connection between wavefront and a ray in optics is called an iconal equation. Okay. So read up about that. In fact, you can also write iconal approximation. In quantum mechanics, you study what is called iconal approximation. So read about that a little. So basically, the iconal equation is that gives you the connection between wavefront and ray in geometrical optics. So it's kind of a nice feature that you see. But now we want to actually use this idea of how is the wavefront, in simple terms, how is a ray determined using a wavefront? So that's the idea I want to exploit here, and because we are doing curvilinear coordinates. So let's see. So let's think of the gradient of it. Okay, so let's think of a function f of x comma y, and let this function be x squared plus y squared. How will this function look like?
Or look like
Geometrically?
Circle?
Yeah, that's a good representation, but this is the radius of the circle, right? So if you were to draw, so idea is to remember that x squared plus y squared is equal to r squared, right? So this is kind of the radius of the circle, right? So if you are in a plane x and y, so you construct this radius at any point, and then you ask, how will that circle of that particular radius will look like? So that's what it will. But for us, this is just a function, right? But good point. I wanted to get the geometry of that. Yeah, this is related to a circle, correct? Now, tell me or calculate what is gradient of f? What does gradient mean? Derivative. And what's the geometry that comes to? What's the insight? What feature of a circle? I said this is a circle. What feature of a circle is the gradient of this function? What do you mean by gradient of a function?
Is it looking for a source? Or
Looking for a source?
Or divergence when we're looking for a source?
No, yeah, divergence looks for a source, good point. But we're talking about gradient, right? So the question is here, how do I say it without missing the answer? Yeah, like if you're doing one dimension, correct? So if you're doing x, and if I were to have f of x, and if I ask you what's the derivative here, also that's a tangent. Right? Tangent is the geometrical. Of course, if I can do a calculation if I'm given a actual functional form, but geometrically that's so. There's an intuition that is important in that. What's the gradient of that function? If I have a function that represents a valley or a mountain, what exactly is?
So if I'm in a mountain, the gradient of function will tell me which way I will go faster to the downside.
Very good, very good. That's a good interpretation. That what Hriday is telling is that let's say if you have x and y, right, and let's say if so this is a contour. Is that clear what this means? So this is actually, let's say this point here is f is equal to let's say 5. This might be 3. This might be 2. Is that clear what I'm doing? That's a contour. Like everywhere along this line, the function value of this is 5. Then it goes down. Then it goes further down. And then you can ask, what does the derivative mean? Okay, but I have only one point. I can calculate the derivative in all directions, right? I can calculate the derivative in this direction, derivative in that direction, and it will have different values in different directions. But what Hriday is saying is that out of all this, one of them will be the largest. Pick the largest of them, and that's the gradient.
Steepest descent.
Steepest descent. Very good. Very good. Okay. So descent or the other way also. Okay. Great. Very good. Okay. So, and that's exactly what gradient is. But there is another meaning of gradient, which is what we want to use here. This is great. This is perfect. That's good. I should also add, or we will learn this in this course. So I'll put this as a quiz at this point. There's a second quiz, right? So let's say this is x and y. This is an actual real plane, like a plane, where a two-dimensional plane in the real space, right? There is also another plane we can think of where this is a complex plane, z. This is the complex plane where this is the real part of z, and that's the imaginary part of z. Is there any difference between this and that as far as geometry goes?
No, they're perpendicular to the x, and real or imaginary part is perpendicular.
So it seems like that should be a one-to-one. When you add, if you had a vector here and a vector here, addition of complex numbers is very much like adding vector, right?
Yeah.
The real part of x adds up, real part of y adds up, right? That seems good. What about multiplication? Right, multiplication here, there is a procedure for multiplication, complex number. Here it's different, right? It's not the same. Okay, so it's not identical, correct? So then one should ask, okay, so gradient here or a derivative So whenever we are doing some physics, typically we are interested in derivative. That's a very nice concept we learned or we built, or Newton helps us build it. And we always think of calculus, right? If we change a little bit in a certain direction, what happens? And this is the calculus of this plane, right? That tells us something about the plane, right? So there is a lot of algebra that went into all the properties of our operations, decided that. What would be the gradient or the derivative, if you want, in a complex plane? Okay. Or tell me next time, what's the derivative when you come from in this, or we were going out, right? What's the derivative in this direction, this direction, this direction, this direction, and so on? What's the directional dependence of a derivative on a complex plane? How is it different from this? Is that question clear?
What is the directional derivative?
What's the directional sense of a derivative on a complex plane? Like the direction, derivative is dependent on the direction on a plane. Correct? As you said, if you go in different directions, you get different derivatives, right? And gradient picks out one of them, but gradient actually at each point, if I were to have this vector, that's not the gradient. Is that the same here also? Does it have a directional derivative? Like, why don't we write do we write a gradient in complex plane? Like, we never study that, right? What do you mean by gradient of a z? Think of that, okay, and just explore that. And we will study this in the course in more detail, but for now, that's it, okay. So, but we will have a better, another meaning for gradient here, which will be useful in this context, but the steepest descent is perfectly fine. And that is that this is normal to the surface. So there is a surface here, right? So there is an X and a Y. And I can plot F on the third axis. Right? When X and Y is equal to 0, this value is 0. Right? When X and Y increases, this value increases. Right? So somewhere it becomes here. So this keeps increasing. Right? In fact, it roughly, so this is, how does this increase? Yes, that's increases like this, right? Okay. So is that clear? What I mean, this is like a, so for a given X and Y, you always have a functional value. But we want to keep in X and Y itself. If I were, the idea is to stay in X and Y itself. Here I have gone outside my X and Y, right? Just to represent my function. So I want to talk about what is X squared plus Y squared. And what we want to do is we are changing F. So let's keep X and Y the same, keep anything constant. So let's say X squared plus Y squared is a constant. What does that mean? That represents a surface typically, or a surface. If this is in 2 dimensions, you typically have a surface. If I make that a constant, it becomes a line. Right? X and 2 variables make a surface. If I fix one of them, then I get a line. It doesn't have to be a straight line. I get a curve in principle. Correct? I get a curve. So this is an equation of a curve. I'm changing the curve. So what it means is that if I had X squared plus Y, this was one circle. And if I change this a little bit, this is the change. Right? So this circle represents when this is equal to constant. If I change this constant a little, it increases to the other side, or it could decrease also. Right? This constant represents F. And we are asking the question, how does this change? How does this constant change as you move around? Right? If I go in a certain direction, how is this changing? So how is this function changing? Or what we mean is that how is this wavefront changing, right? The gradient of that will be always normal to that. So the idea is that if you can imagine the surface, always that may not be easy to imagine, but first put in some effort to imagine the surface geometrically. This will always be normal to the surface. Surface, if it is in 3 dimensions, if it is 2 dimensions, this will be a curve, right? Like it's a circle in this case, right? The surface F is equal to a constant. It's like saying if this represented the temperature in our room, right? So if I say where is the surface of exact 76 degree Fahrenheit, 76 is approximately 25 degrees Celsius, right? So you have to pick all the points in this room where it is exactly 25 degrees Celsius, right? So if this point has 25 degrees Celsius and there is a light source there, that might be 26, right? That might be 27, and it will get hotter and hotter as I get. So there is a surface somewhere here where it's exactly 25 degrees Celsius. Is that clear what I mean? And normal to that surface is a gradient. Okay, so that's one way of interpreting a gradient. And that's what we want to use here, Christian.
So the normal will be different at different points of the surface.
Correct, correct. Very good. So at different points, it will be different. So that's your normal, right? It's different in different places. So it is position dependent. Correct. Very good. Agreed. That's important. Yeah. That's a geometrical picture. So now let's see what's the connection between all this. We will say that a ray, so F here will represent a wavefront. And the moment I have a wavefront, I can get a ray out of it. That's a gradient of F. Okay. This will have we are going to define some things here today. This will be called a contravariant. So this is not exactly the same. There is a this gives you a physical insight how to imagine things, right? So I'm going to define a few things, and this will be the analogy for that. This will be called a this will be the analogy to contravariant vector, and this will be a covariant vector. We'll define that very quickly. Good. Okay, with all that ideas, so let's proceed and define a few things. Or again, one more picture might help. Let us say, again, coordinate system, the main idea is to make sure that one point in a plane is uniquely specified by 2 coordinates. Right? So for example, this is a way, if I want to specify every point, rectangular coordinates tells that, okay, give me a line. So, x is equal to 3. So x equal to 3 means it's somewhere on that line. And then you say that, okay, where on x equal to 3? Oh, y is equal to 4. Well, that's y equal to 4. And that means this is the point. So rectangular coordinates basically specify a point in the plane. You can also do this in various other ways, right? So I can do this to be my coordinates, some curve like this, okay? But then I need, if I say that, oh, this is, let's say u is equal to 1, u equal to 2, u equal to 3. The moment I say u equal to 2, it could be anywhere on this line, on this curve. And I want to specify something more. So I would say, oh, I want to specify one more curve, one more family of curves. Right. So this is, let's say, uv, right? V is equal to 1, v is equal to 2, v is equal to 3. And again, this could be a point in here. So a coordinate system is basically picking a coordinate. But now the idea is that, oh, you don't have to do that. the moment you talk about curves, that's a wavefront. I can talk about a ray. For every, so think of this lines. I'm going to draw perpendicular to that, right? That's gradient. So I'm going to draw perpendicular to that. So that's my same color. I thought it would be right. That's my ray, right? If you can imagine that, so get rid of that earlier version and get this new rays. That's the perpendicular lines corresponding to you. And now get the perpendicular lines to this also, right? So I'll have this. They're divergent, like in the sense they're growing out. And the intersection of these lines, right? So for example, this is an intersection, that's right, this is an intersection, right? That's also a coordinate system. So the moment I have a family of lines, I can draw gradient of them and they form a new family of lines or curves, right? Either one of them is good. And in fact, these two have a very close relation. You use the word dual. That's exactly what it is. That is a dual relationship. You can actually, there is a strong correspondence. That's what we will see, okay? So let's see what's, so that's the geometrical picture you want to have. So now let's do the concrete thing. Let's take specific definitions for all this. So let's define, we are now going to define covariant vector. Let's have a vector R in 2 dimensions or 3 dimensions R, and we are not going to work in, we don't even know what rectangular coordinates is, let's say. We are just starting with any random coordinate system, and the coordinate system is U1, U2, U3. In some basis, which we are going to define, so these are the family of lines, right? U1 is equal to constant, U2 is equal to a constant, U3 is equal to a constant, correct? So this means family of curves, let's say, family of surfaces, right? That's a family of surfaces. U1 is equal to a constant, U2 is equal to a constant, U3 is equal to a constant. Is that clear what I mean? So I talked about 2 family of surfaces. This is a specific example could be in cylindrical coordinates. We are talking about rho is equal to x squared plus y squared. Right? So this is your U1 in cylindrical coordinates. Right? The radius of, so these are circles. Right? And the other coordinate, U2, could be phi, which is in terms of x and y, tangent inverse of y over x. Yeah. Remember again, this is a convenience that we can express things in terms of rectangular coordinates. Right? So this is what it means, rho and phi. And this is a geometrical idea of the coordinate. Like our goal is to specify the coordinate. This represents the coordinate, the geometry of that coordinate. This is a point, just the geometrical insight into that. Okay, so what is a covariant vector? A covariant basis vectors. So I should say this is covariant basis vectors. Yes, covariant basis vectors is going to be. Now notice I'm using an arrow on top and an index below. I'm using a mixed notation. This arrow should have a new index. So it's a tensor basically I'm talking about. Okay, but just for clarity or specific, giving an insight of what that second index means, I'm writing a vector and an index. So I'm mixing up the 2 notations. Okay, so this is going to be defined as how these coordinates change with respect to the surfaces. That's going to be my definition of the covariant basis vectors. Immediately, since we said we are in cylindrical coordinates or two-dimensional cylindrical coordinate, let's see what this means, right? Let's quickly do this. So this is E1, vector E1 will be equal to the how are changes with respect to rho. Correct? Because U1 was rho, right? I have set I is equal to 1, I is equal to 1. I1, U equal to 1 was rho. Right? This is an example, that's your definition. This is clarifying, like an illustration of what that definition is. We can, since like usually we have to do this geometrically, but to proceed, it is good to connect it with rectangular coordinates, pretending that rectangular coordinates is known. R is actually equal to X I hat plus Y J hat in rectangular coordinates. And I'm interested in the cylindrical coordinates. Write it in terms of cylindrical coordinates. This is rho cosine phi in the I hat direction plus rho sine phi in the J hat direction. Right? Then I can immediately do this derivative. Correct? And how much is this? This is equal to, I know how to take the derivative of with respect to rho. So this is cosine phi I hat plus sine phi J hat. And what is that equal to? What's that? How does that vector look like?
Exponential idea.
No.
No, it's different.
Because it's in a complex plane, correct? Yeah. Good point. But how does that vector look like? What's the magnitude of the vector? One, right? Yeah, sine square plus cosine square is 1. What's the direction of that vector? What's the direction of this? Or what's R vector R divided by the magnitude of this vector?
Magnitude is 1.
No, for this. That's vector R. Magnitude is, magnitude of this vector is 1. Correct. Magnitude of this is rho, right? If I divide by rho, what do you get?
1.
If I divide by rho is gone, right? And that is cosine phi sine phi. That's this vector, right? This vector divided by R. So this is R hat, right? This is R hat because vector divided by R. This is R hat. A unit vector in cylindrical coordinates, which is, if I were to draw this, right? It's everywhere radially outside. Correct? That's your unit vector. So E1 is your unit vector in your cylindrical coordinates. Let's do E2. By definition, this is the R by D5. Okay. What's that? Can you evaluate that?
Minus sine theta.
Yeah, this one, right?
Rho minus rho cos.
So this is minus rho sine phi. I have direction plus rho sine phi. Right? Okay, that's good. What's the magnitude of this? Magnitude?
Again consider
Rho, right? Not rho squared, it's rho, right? So it's not unit vector. This is not a unit vector. Right? But what if I talk about define E2 hat, which will be E2 divided by E2, right? What is that? So I have we're talking about cylindrical coordinates now. Cylindrical coordinates, I said that always coordinate systems are built out of surfaces or curves here. Like cylindrical coordinates are built out of family of curves of circles of different radius. That's one of them. That was the easy one. What's the other curve? There is a family of curves that represents as they intersect this, right? This is rho equal to a constant. Phi equal to constant is the other one. Where is phi equal to a constant? If I set my angle to be a constant, what curve does it represent? Angle is constant. Which curve has angle equal to a constant? So how will you plot phi equal to a constant here? Phi equal to a constant is a half line. Right? Phi equal to a constant. Correct? Is that clear?
Yeah.
If I change that, phi equal to a constant, half line though. I cannot go in beyond that. Right? Phi equal to a constant, phi equal to a constant, phi equal to a constant, phi equal to a constant. And intersection of these lines is what cylindrical coordinates is, right? Intersection is here. Right? Rho phi, when we say, oh, that's that point. But I'm interested in vectors now. I'm interested in the basis vectors. I know that this is r hat, as you said, this is point dependent, right? So this is my r hat. R hat, everywhere if I change. Where is my E2 hat, which I will call here phi hat, because we are working in cylindrical coordinates. Where is my phi hat? Phi hat is perpendicular to the curve that describes that. So that's your phi hat. So if I were to, let me clarify this on a single curve, at some point here, that's my rho hat, and that's my phi hat. Is that clear?
So
Phi
one is normal and another one is tangent.
to the circle.
Yeah.
Both are normal to their surfaces. Rho hat is perpendicular to the circle. And phi hat is perpendicular to this line. Right?
Yeah.
Both are perpendicular. Either you can think of it as both are tangent to certain things, or they're perpendicular to things. Right? In this case, when we think of the curves, like for example, phi hat is perpendicular to the phi equal to a constant. Right? How does, as you change your coordinate with respect to phi, how does that vector, in what direction is it changing? Right? That's what this. But now we'll go to the tangent one, and that will be the other basis vector. Okay, is that clear?
Yeah.
So now we defined two things here. So let's quickly now go. So that's your covariant basis vectors. Right? So now let's. So now let's define what is called contravariant. Basis vectors. Contravariant basis vectors will be defined as E with a superscript, and that's different. Okay, by construction, both will be different. Okay, one is called covariant, which is down, and contravariant is up. This will be defined as gradient when I say gradient with respect to x and y, right? This is d by dr, right? I'll write that in a minute. Of u of I. Again, these are two vectors. This is a tensor in principle. This is a j and that's a I. It's tensor, but I'm mixing it. Like one I'm writing it as a vector, one I'm writing it as an index, just to get some insight. And this should be thought of as, oh, where is my r here? This is actually d by dr. How do the coordinates change with respect to my coordinate, or how do the surfaces change with respect to the coordinate? But that's very easy. We know how to understand gradients now, right? So there's a geometrical picture. Let's just do this now manually. Let's say E1, right? In cylindrical coordinates represents gradient of rho. I told you that, oh, this is a gradient is perpendicular to that. We immediately know that this is going to be in the rho hat direction, correct? Perpendicular to that. But let's specifically do this. Right? This is equal to I hat d by dx plus j hat d by dy of rho, where rho is x squared plus y squared. This is derivative brings things down. So this is I hat times 1 by 2 times 2x over x squared plus y squared plus j hat 2y over 2 times x squared plus y squared. Okay. If you do this derivative, 2 cancels out, x cancels out. That's the same as xi hat over x squared plus y squared is nothing but rho, right? So that's rho, and this is y j hat. And that's again vector rho, if you want x and y, divided by rho, that's equal to rho hat again. So this time, notice it is tangent. The contravariant to that circles is tangent to the, if you want, tangent to the phi curves. Earlier we were getting normals to that, this time it is tangents, right? So as a dual nature in this. So let's quickly do the other one also. Let's do E2. That's gradient of phi. That's equal to I hat d phi by dx plus j hat d phi by dy. But phi, what is phi? Y over x. We can do this and show that this is your quiz. This is the third quiz for today. Finish this quiz. I want to go a little faster in the last 10 minutes, not even 10 minutes. Okay. This comes out to be equal to phi hat over rho. Okay. So you have to show that, you have to complete that. Is that clear? You have to take the derivative of tan inverse of y over x. When you're taking the derivative with respect to x, y is equal to a constant. Very clear?
Yeah.
Question? Okay. So that's your two basis vectors now. Any questions? Can I proceed? Yeah.
Yes.
Okay. So, So I have two basis vectors, right? There is E1, that is E2, right? Which is basically EI. Right? And there is another set of basis vectors. Let me say two of this, and there is another set of basis vectors which is E1 and E2. Contravariant, covariant. Correct? If I have two sets of vectors, I can put them together, right? This is like a tensor. I can contract them. I can make a dot product with them. So let's build, there's a lot of possibilities, right? I can do this dot product, this dot product. So let me write this as E1 dotted with E1. Okay, I want to calculate that. E1 dotted with E2. Calculate that. E2 dotted with E1. Calculate that. E2 dotted with E2. Only four numbers. And the remarkable thing, this is the interesting part about the whole definition of tangent vectors and normal vectors, is that whichever geometry you're in, whichever coordinates you're in, doesn't matter. This will always come out to be 1, 1, 0, 0. It will always be diagonal. That's the advantage of defining these contravariant covariant vectors. Okay. This, we will simplify this as, we will write this whole information as EI dotted with EJ will be equal to, what will you write on the right hand side? Delta IJ. This information of 0, 0, 1, 1 is the same as delta IJ. Right? Perfect. Okay, very good. This is called orthogonality. Okay, so this is called orthogonality. But this is more than just the standard orthogonality we see in coordinate system, in the sense this is intrinsically, like intrinsically, if I take one covariant, other contravariant, it will always be orthogonal. So that's an advantage there. In your homework, you will do what is done in crystallography. In crystallography, basically, you have some symmetry you see in the real space, but then you go into what is called a momentum space or a reciprocal basis. That new symmetry, the reciprocal basis, is your contravariant vector. Covariant vector is what you see in real space. The other one is your reciprocal basis. Or you might have heard of Fourier transform. You work in the position basis, then you go into momentum basis. That's what we are talking about here. Like, there's a connection between all these quantities, and there are intrinsically they're perpendicular. So this is called a scalar product. You can define it, and it will come out to be always orthogonal. So that's okay. So again, quiz, right? You have to check this out. So lots of quizzes. Fourth quiz, complete this. You have to show that this is actually 0, 0, 1, 1. Right. These things, if you want to finish, if you get stuck by any chance, it is not working, you can go to the earlier last year's lectures, and there I complete that. Here, I was supposed to start it on last Friday, remember? So I usually go slow in this, I'm jumping steps. That's okay, that's good. Okay, so that's your orthogonality. But let's also define something more, and that is going to be what if I actually don't. So notice here there is a very special thing I've done, right? One is from covariant, other is from contravariant. I didn't have to do that. What if I do both in the same space? What if I were to do EI dotted with EJ? That's also a quantity I can build. And what does that represent? This is what we will call a metric. So this will be called Gij, and this will be defined to be the metric. Find the metric in the cylindrical coordinate, but then I don't have to be in covariant basis. I can also be in the contravariant basis, and that will be I dotted with J. And let me stop there. Like you will see these definitions more in a very simple scenario, not in cylindrical coordinates in your homework. So I choose lines itself, but oblique lines. Like you don't have to have an orthogonal system. You have an angular coordinate. They are not orthogonal. And then I ask you to calculate this first. Then I ask you to calculate this. So it's a little tedious, but look for orthogonality, look for metric, and then you will also do for, so I define what is called completeness and so on. So, but you just have to mechanically do it. So keep doing that. And if you get stuck, look into the lecture notes from last time, but I will fill in on Friday anyway. But I think you can finish it even though I haven't completely taught it. Just go by the, and I describe it pretty much in detail. If you're stuck, meet me, okay? We can always postpone. And let me stop here because you guys are very close. Yeah. Thank you. Okay. Is the pace going okay? Am I going fast?